Do you remember this result from Herstein's topics in algebra in the 4th chapter where we study vector spaces? There we came across this result, and everything about dimensions of finite dimensional vector spaces depends on this. So let's just go through the result and let's see its proof. There is something wrong with this. The result was fairly simple. We have a vector space V over some field F, and these are some finitely many vectors in V. N vectors are there. Then either they are linearly independent or some vector Vk is a linear combination of the preceding vectors V1, V2 up to Vk minus 1. Let's go through the proof briefly. Essentially, what the proof did is this. If the given vectors are linearly independent, then we are done. Of course, because that's a part of the conclusion. If they are linearly independent, there is nothing else to do. So suppose that they are not linearly independent. That means they are linearly dependent, which means that there will be some scalars alpha I using which you can form the this linear combination of the given vectors that become 0, and where all the alpha i's are not 0, because that is linear dependence. Not all alpha i's equal the 0 scalar. So we are looking at finitely many scalars, not all of which are 0. This means that there will be a largest index k in the range from 1 through n, such that alpha k is not equal to 0, which means that the other alphas which come with indices greater than k, alpha I, where I is greater than k, those alpha i's are 0. This is the coefficient having largest index which is not 0. Then the other terms which appear after this kth term will vanish, they are not going to be there. So this equation reduces to this form: alpha 1 V1 alpha k minus 1 Vk minus 1 plus alpha k Vk, that is equal to 0, and we know that alpha k is not equal to 0. What does the proof do after this? Let me continue from here. After this, the proof takes all the Vi's that come before Vk to that other side. So we will then have alpha k Vk equal to minus alpha 1 V1 minus alpha 2 V2, like that it will go, minus alpha k minus 1 Vk minus 1. And then because alpha k is the non-zero scalar, it's the non-zero field element, so its multiplicative inverse exists in the field. And that then gives us this. alpha k inverse alpha 1 v1 minus alpha k inverse alpha 2 v2, and finally this. Okay, so that way you obtain vk as a linear combination of the preceding vectors. However, do you notice something wrong with this? Are we not assuming here that k is greater than 1? What is k? K is the largest index for which the coefficient is not equal to 0. What if k is itself 1? What will happen then? If this k is 1, suppose k is equal to 1, then this reduces to what? Now the higher coefficients, that is alpha I, where I is greater than 1, they are all 0, and that's why those are not present. And the above equation reduces to this: alpha 1 v1 is equal to 0. Now, alpha 1 is not 0. So, if you multiply both sides of this equation by the inverse of alpha 1, multiplicative inverse of the scalar alpha 1, then using the vector space properties, you get this. v1 equal to 0. But are you getting v1 as a linear combination of the preceding ones? There are no vectors that come before v1. So is it not something wrong with this proof? I mean, if you just carelessly, simply, without even mentioning, you assume that k has to be greater than 1, and you complete the proof like this, I don't think it's correct. And in fact, to make it more clear that something really is wrong, let me now take a specific such list of vectors in V, this list. That will more clearly show that yes, something indeed is wrong. Suppose we have this statement, this claim. Note that no condition is imposed on these vectors. These are just some finitely many vectors in V. Okay. So we have our V, now also we have our V. But now let me take this. So this is my V1. V1 is 0 and V2 is some V where this is not equal to 0. Now, can this set be linearly independent? Is it linearly independent? The answer is no. Why? That's because you can choose the scalar 1, the unit element from the field, multiply the 0 vector by that, and you can choose the scalar 0, the 0 element of the field, and multiply the vector v by that. This is a non-trivial linear combination of 0 and v because of this non-zero scalar. However, this is equal to 0. So that is why this set is linearly dependent. In other words, it's not linearly independent. So the one half of this claim is not true for this set. Then according to this, the other half should be true because that's the theorem, right? So, some vector in this set should be a linear combination of the preceding ones. Is V a linear combination of 0? That's not possible. You multiply the 0 vector by any scalar lambda by one of the elementary properties of vector spaces. This will be 0, but V is not 0. Okay, so V is not a linear combination of the preceding ones. There is only one such vector which comes before V, and V is not a scalar multiple of that. But then, can we say that 0 is a linear combination of the preceding ones if we interpret this statement like this? Because there are no vectors that come before 0, so the statement that 0 is a linear combination of the preceding vectors is vacuously true. You can consider this statement like this. If there are vectors that come before 0, then 0 is a linear combination of them, and that implication is vacuously true. Say I assume that this representation is this interpretation is to be adopted to save this theorem in this case, because we want the theorem to be true, right? But then the theorem itself loses value. Why? What is the theorem saying? The theorem is saying that if we are given a finite list of vectors in a vector space V, then either they form a linearly independent set or some Vk is a linear combination of the preceding ones. Now with this new interpretation, which allows us to say that 0 is a linear combination of the preceding ones because there are no vectors before 0, we can apply this interpretation to V1. V1 is always a linear combination of the preceding ones because there are no vectors before V1. And you can say that this statement is vacuously true regardless of whether this list of vectors forms a dependent set or an independent set. Do you see how stupid it looks if we allow that interpretation? That means something is wrong, and it's actually wrong. On one hand, if we do not consider that interpretation, then here the theorem fails, it's not true. But if we do consider that interpretation, then the theorem loses its value in the sense that it just does not really tell us anything useful. So what do? So now I am going to slightly modify the theorem like this. I will make two changes to that statement. So this is our new theorem. For to 1 star, let again we have finitely many vectors, but this time none of the vectors is 0. Okay. Then either they are linearly independent or Vk is a linear combination of the preceding ones for some k that is greater than 1 and less than or equal to n, of course. These are the two changes I have made to that. One of them is this and the other one is this. Here we are clearly mentioning that k has to be greater than 1. Now let's see if we can create a proof of this similar to that previous proof, but this time the proof should not have any such ambiguity in it, that it's not saying something clearly. Let's see. It should be absolutely clear that the proof has no gap. Okay. So we will start similarly. What is our claim? The claim is almost the same. Either these vectors form a linearly independent set, or some vk is a linear combination of the preceding ones, but with this extra condition. And also now none of these vectors is 0. This we assume primarily to avoid that situation where we consider that set which has 1, 0. Okay, so let's now see. Proof. If these are linearly independent, then we are done. Otherwise, they are linearly dependent and what will happen in that case? As before, there will exist scalars, not all 0, such that I'm not writing very systematically, okay? I mean, you understand. If you want to write this proof, then you can supply the missing lines, statements. I'm just showing you the main idea. Alpha n Vn is equal to 0, where not all the alpha i's equal the 0 scalar. Okay. And as before, let k be the largest index such that alpha k is not equal to 0. Now we are going to see that we cannot take k equal to 1. If we suppose that k is equal to 1, then the above equation reduces to alpha 1 v1 equal to 0. But do you remember the hypothesis? None of these vn's is equal to 0. Now alpha 1 is also not 0, obviously, because alpha k is non-zero, and if k is 1, then alpha 1 is not equal to 0. Since alpha 1 is non-zero, alpha inverse in F exists. So V1, which can also be written as 1 V1 by the fourth vector space axiom, that becomes alpha 1 inverse alpha 1 v1, and then by the third axiom this is alpha 1 inverse alpha 1 v1. Now alpha 1 v1 is 0, is the 0 vector, and by one property of vector spaces, one elementary property, this product is the 0 vector. But this is a contradiction. It contradicts the fact that v1 is non-zero. It's a contradiction. And that is why we cannot suppose that k is equal to 1. So, k must be greater than 1. And because k is now greater than 1, actually there exist vectors before vk. Okay, so it's not that there is no vector that precedes vk. There are vectors that precede vk, at least one. And that is why the rest of the proof now follows easily. And there is no gap in this. So, you have to modify the statement in topics in algebra. The statement of this theorem 4 to 1, you have to modify that like this. And this modification will cause some small changes in the consequences of this theorem, which are its corollaries, and some little things need to be changed in the theorems and corollaries which come after this. That we will discuss about in another video. Okay, so I just suddenly noticed this and I got really disturbed by this. But now it's okay. And I have been able to change the other subsequent results based on this successfully. It's not a very big thing, but what is not true, what is incorrect, and it needs to be rectified. So that's just it in this video. So I just wanted to make this small video. And tomorrow, of course, we have our calculus video.